Welcome to 8.2, Equations of Planes. So just to get us in the right frame of mind, we are very used to, very confident working in two-dimensional space using our coordinate plane. Now this is called a coordinate plane because it is a two-dimensional space that expands infinitely in all directions. Okay, that's why we have our arrows here, left and right, and up and down. So this is a plane with two coordinates defining any point in the plane. You can draw points, you can draw lines, but all of these things lie on the same plane. It's a flat, perfectly flat surface in two-dimensional space. Now what happens when we move into three-dimensional space? Well, we can still talk about points and lines and planes, but there are an infinite number of planes that you can talk about. So let's just take this concept of the xy plane. Well, we have an x-axis and a y-axis here as well. So what does the xy plane look like on a three-dimensional grid? Okay, it looks something like this. This whole flat surface dictated by the x and y axes that can also then be pulled up and lift that plane up, or it can be pushed down, pushing that plane down. Now that plane would be parallel to the xy plane, but it might have a z coordinates that pull it up or that pull it down. And you could do that with anything. You could think about the other planes on here. You could do a plane that's parallel to the ZY plane. You could do a plane that's parallel to the ZX plane. Okay, but all we want to get at right now, and we're going to look at all those different planes and how to write equations for them and how to define them. But all we want to know right now is that the plane is a two-dimensional space that expands in every direction infinitely. It is perfectly flat. It has no depth. All right, I'd like to talk through the investigation that's in our textbook for lesson 8.2. And the first section, we're just looking at vertical and horizontal planes. So if you had to guess which of these were vertical and which of these were horizontal, what would you pick? So I can see there's a vertical plane here and a vertical plane here, and this guy is considered our horizontal plane. So we're just going to look at how we created those, and you can see this is a plane that is parallel to the z-axis and parallel to the y-axis. So this plane is parallel to the zy plane, and we can see that it's been pulled in the positive x direction 3 units. Okay, how do I know that? Well, this plane is defined by x equals 3. X equals 3. So as long as x equals 3, y and z can be any two other coordinates, and the point, so these red are points defined by the 3 parameter coordinates here, those points will lie on the plane as long as the value of x is 3. So the equation for this plane is actually x equals 3. Let's take a look at this one. This one has moved up along the z-axis 3 units. And so you can see that every z coordinate is 3. X and y can be any two other coordinates, but the triplet, the ordered triple, will always have a 3 in the z position. So this plane is parallel to the xy plane, and it has been pushed 3 units in the z direction defined by the equation z equals 3. All right, last one is another vertical plane. It's a vertical plane defined by y equals 3. And all the other coordinates, x and z coordinates, can be anything, but as long as y is equal to 3, the point will fall on the plane. This plane is now parallel to the zx plane and defined by the equation y equals 3. These are examples of vertical and horizontal planes. Now you can also see that you could push this this particular plane further back or further forward just by changing the x coordinate. This plane could be pushed up or down just by changing the z coordinate, and this plane can be pushed back or forward in the y direction just by changing the y coordinate. Now, these are just 3 examples. There's lots of examples of planes. They don't have to be horizontal and vertical. They can go any which direction crosswise, and these ones are defined by one parameter, one of the coordinates in the ordered triple, but many times planes are defined by 2 parameters. So that's what we have in our next example. So we have these planes right here, and they still form a plane, and I can see that this plane is parallel to the z-axis, okay, but not to the x or the y-axis. It seems to cut kind of across each of those faces. But I can make a connection between some of these. I see that the x coordinate and the y coordinate in each ordered triple actually have a really strong relationship. They're the same value in each one, okay? So what does that tell me? Well, that tells me that x minus y is 0. So if that's true of all the points on the plane, then that becomes the equation for the plane itself. As long as x minus y equals 0, the point will fall on this plane. And again, you can see z is not involved in this equation, but we could involve z. It would be 0 times z, which means it doesn't matter what your z coordinate is, it's going to be on this plane. Z is not a part of defining the plane. Z can be anything, and any coordinate of z will fall on this plane as long as the x minus the y coordinate is 0. Let's take another look at this one over here. It's a similar situation. It is defined by the relationship between x and y. You can see you have 2 and -2, 2 and -2, 0, 0, -2, 2, -2, 2. Okay, now the 2's aren't particularly important to realize here, except to say that in every situation, x plus y equals 0. Okay, that means z can be anything, and it will still fall on the plane defined by x plus y equals 0. Now we could come up with other points that are on this plane. For instance, if -2, +2, -2 are on the plane, then we could stretch, let's just say we're going to stretch out here. Okay, and this might be something like 4, -4, +4, and whatever the z coordinate is doesn't particularly matter, but let's just say it's 3. Okay, so I just wanted to do an example that didn't use the number 2, but I can still see here that x plus y is 0, and the y coordinate could be anything, and that point still falls on the plane. All right, so again, equations of planes. This plane is defined not by x plus y equals 0 or x minus y equals 0, but x minus y equals 3. And so it cuts across the xy plane. It's parallel to the z axis, and you can kind of see how it's been pulled in this direction. And then we can look at this one, and it's a similar situation. It'd be more difficult for me to draw an arrow to show how this one got pulled, but it's x plus y equals 4. So as long as the x coordinate plus the y coordinate equals 4, then any value of z, doesn't matter, that point will still fall on the plane, okay? So how do we define these planes? Well, they're defined by an equation, but there's other things that like a minimum requirement for defining a specific unique plane, and we're going to get into that right now. Okay, we're going to try to relate the graphing of an equation of a line in 2 space to the graphing of an equation of a plane in 3 space. And so to start, I'm just going to draw us an axis. We have a y and an x axis, and I'm going to graph the line x plus 2y minus 8 equals 0. So this means that there are ordered pairs, x, y, that satisfy the equation, an infinite number of them, and they will all fall on this line. The easiest way for me to draw this is to say, okay, where is the x-intercept that occurs when y equals 0? It's going to be positive 8. 1, 2, 3, 4, 5, 6, 7, 8. And where does the y-intercept occur? It occurs when x is 0, so that's going to be 8 on this side, divided by 2, y equals 4. 1, 2, 3, 4. There's 2 points. If I have 2 points, I can draw a line. Now, it's not super easy to see on mine because I don't have the full grid drawn, but there are many other points that fall on this line. So we already know that point A falls on the line, and it's at 0, 4. And there's a bunch of other ones. I can just kind of put them on here. Let's call them B, C, D, and let's call this one E. We know this, the coordinates of this guy are 8, 0. The coordinates of this guy, we'll move him there. 6, 1. And these all have coordinates that satisfy the equation and lie on this line in two-dimensional space. But we could take this exact same line, this equation, and we could graph it in 3 space. So in 3 space, easiest way to graph things, I can draw the whole superplane or the whole 8-boxed octant thing, but I'm just gonna draw it how our textbook has it. Gives us the best chance of seeing this thing properly. So we have our y-axis, our x-axis, and our z-axis, and again z can go infinitely negative, y can get pushed back, and x can get pushed back as well. But what we want to see here is the graphing of this particular line, and we know 2 of the main points here are our intercept. So our y-intercept is 4. So I'm just going to go 1, 2, 3, 4. And our x-intercept is 8. So we've got 1, 2, 3, 4, 5, 6, 7, 8. And so this line then I can draw through my 2 points. And it goes infinitely in either direction. And in this case, it's lying flat on the xy plane. And z is 0 for every point along this line. That's right, we can add a z coordinate to all of the points along this line. So for instance, this guy right here, we found it, it's the y-intercept, which means that x is 0, y is 4, and in this case, z is 0. Okay, for this point over here, x is 8, y is 0, and z is 0. But our equation does not restrict the value of z. So for instance, this equation, x plus 2y minus 8 equals 0, could also be written x plus 2y plus 0 times z minus 8 equals 0. So here what we've done is we've actually included our z coordinate, our z axis, our height, I suppose you could call it, on our 3-dimensional drawing here. The only thing that has to be true is that x and y have a special relationship. X plus 2y has to equal 8. Okay, that's really what's happening. But z can be anything at all, because if we multiply it by 0, this term just becomes 0 and doesn't change the equation at all. So what happens here is that z can actually be any point. So this is on here, but if I move it up by 1z, that point is on there too. And if I move it up 2 in the z direction, 8, 0, 2 is also on this, and 8, 0, 3, and 8, 0, 4. What about all of these other points along the line that we drew? What about the point D at 6, 1? Well, that's over here, 6, 1. Now this point is on our 3-dimensional plane. Actually, I should draw it actually on the line where it belongs. Okay, 6, 1, D 6, 1, but now this point is actually 6, 1, 0, and I can build any other points by just moving that up. I can change the z coordinate of that point, and I can move it down below the line as well, and I can do that to any other point along the line. All of these points and every point in between also satisfy the new three-dimensional equation that we've constructed, and you can see what's beginning to form in my drawing is that we actually are forming a plane. Okay? And this plane extends infinitely in all four directions, and it runs parallel to the z-axis, and z can be any value because the equation is only determined by the relationship between x and y. So one way of generalizing what we did here, okay, I took the point 0, 4, and on the original line it was 0, 4, 0, but in order to satisfy this equation, this point can be really represented, not this point, but the value of points, the infinite possibility of points can be represented as 0, 4, z. This relationship has to hold true according to the equation, but z can be anything at all. Same thing with all of these points. They can be represented by 6, 1, z. Okay? The relationship between the x and y coordinate has to hold true according to the equation, but z is free to be anything that it wants, and we will still be able to plot that point on this plane. So in general, what did we do? We defined the scalar equation. It's very much like the standard equation of a line in two-dimensional space. So the scalar equation of a plane is, it's going to be familiar, ax plus by plus cz equals 0. And again, we can define a plane using just one of these parameters or two of them, or the relationship between three of them, and then you'd get some like kind of crossing all three axes and planes and moving it any which direction. Okay, heading into example 1, it's just getting us used to working with planes, and so we're going to be given an equation of a plane. We're going to consider the plane defined by the scalar equation x plus 2y minus z minus 8 equals 0. And what do we need to do? So you can see here that each of the parameters, not any of the three has a coefficient of 0. So they're all involved in figuring out which points are going to be on this line, and that's what our first point is. We're going to decide are the points A, and we'll define these points. We're going to determine if these are on the plane or not. 1, 3, -1. And I'm just going to do two of them. There's 3 in the textbook, but B, 3, 5, 1 on the plane. All right, let's take that one on first. There's going to be 4 parts of this example. Probably takes about a full page. So are these points on the plane? Well, if they're on the plane, the coordinates x, y, z need to satisfy this equation. Okay, so we're just going to check for A whether or not x equals 1, y equals 3, z equals -1 will satisfy the equation. We'll make this equation remain true. We're going to do that using a left side, right side strategy. The left side is all we're going to write because the right side is 0. But the left side is x plus 2y minus z. All right, I'll sub in what I know. I know x is 1. 2 times 3 is y is 3. And minus -1, that's going to be plus 1. Well, this is not 0. This is 6 plus 2 is... sorry. It is going to work. Sorry, I missed this -8. Hopefully you caught that. So we've got 6 plus 2 is 8, minus 8, that's 0. That does equal the right side. Therefore, the point A is on the plane. Okay, let's check B. We've got our left side of the equation. I'm going to write it properly this time. X plus 2y minus z minus 8. Sub in what I know. X is 3, y is 5, z is 1. I've got 10 plus 3 is 13, minus 1 is 12, that's 4. And that does not equal the right side. Therefore, the point B is not on the plane defined by this equation. In the second part of this example, we're going to find the intercepts. So we're going to find the X-Int, the Y-Int, and the Z-intercept. And just like we do using linear equations, we're going to set the other two coordinates to 0, the other two parameters to 0. So for finding the x-intercept, we need to set y and z equal to 0. Okay? So I'll write it out the first time. I won't write it out every time, but we've got x plus 2y minus z minus 8 equals 0. We're going to set y to 0 and z to 0. We end up with x minus 8 equals 0, x equals 8. So the x-intercept then is positive 8. For the y-intercept, we're going to set x equal to 0 and z equal to 0. That's going to leave us with 2y minus 8 equals 0. 2y equals 8. Divide both sides by 2. The y-intercept then is 4. For the z-intercept, we're going to do the same thing. We're left with negative z minus 8 equals 0. Negative z, maybe I'll do it the other way so I can do it in one step. That's just going to give me z equals negative 8. I'm going to be adding z to both sides there. Z equals negative 8, so that is our z-intercept here. I'm going to clear this and we'll head on to part C. In C, we're asked to determine the coordinates of another point on the plane. Okay, we've defined a few of the points on the plane. We found A was on the plane. We also found the X, Y, and Z intercepts. Those are 3 other points that are on the plane. But just like a line has an infinite number of points, a plane also has an infinite number of points. And in order to find points that are on the plane, all you have to do is choose arbitrary values for 2 of the variables, and then choose use algebra to find out what the value of the last variable has to be in order to satisfy the equation. So again, you can set a value for x and y, any value you want, any 2 values, same value, different value, doesn't matter. You'll be able to find out what z has to be to put that point on the plane. Or you could set a value for y and z and figure out what x has to be in that case, okay? So I'm just going to find one, and it doesn't matter what we do. So let's let x equal 2, and let's let y equal negative 3. Again, arbitrary values. So what do? Well, I have x plus 2y minus z minus 8 equals 0. That statement has to remain true. Well, if x is 2, I have 2 plus, and y is negative 3. Now I have an equation, one equation, and the only variable left is z. So I can figure out what z has to be to make this equation true. Okay, so here we go. We've got 2 plus negative 6. Okay, so 2 minus 6 is negative 4. Minus 8 more is negative 12. So I've got negative z minus 12 equals 0. I'm going to add z to both sides. That tells me that z if x is 2 and y is -3, z has to be -12 in order to maintain this truth claim, in order to satisfy the equation. So what does that tell me? It tells me, therefore, the point 2, -3, -12 is on the plane. And again, you could have chosen any of the two variables to set the value for, and then use algebra to find that third variable that will satisfy the equation. In part D, we're going to write two vectors that are parallel to the plane. Or we'll just say this, vectors parallel to the plane. In order to do this, we need a bit more information. So we actually had these points given to us at the beginning. Point 1, 3, -1 was point A, which we determined was on the plane. And then I did B, which was not on the plane, but point C was also on the plane. Point 1, 6, 5 is on the plane. So if we're looking for vectors that are parallel to the plane, it simply means that, the plane goes in 4 directions in 2 dimensions out, right? Infinitely. So a vector that lies on that plane will certainly be parallel to the plane, okay? So if you have a plane and you have a vector lying on the plane, that vector will be parallel to the plane. But you could also have a vector that is lifted off of the plane and is above the plane and still heading the same direction out as this vector. It's just been moved up. If it's parallel to a vector that's parallel to the plane, then the new vector is also going to be parallel to the plane. While it's not on the plane, it is parallel to the plane. So one really easy vector that we can come up with that is parallel to the plane is the vector AC. And that's because A and C are both on the plane. So in effect, we're just taking a vector between 2 points on a plane. That vector is on the plane. It therefore is parallel to the plane. So to find the vector AC, we're going to go from C to A. So we're going to take the coordinates of vector C and the difference between A and C. We're going to subtract A, 1, 3, -1. And the vector AC then is 1 minus 1, 6 minus 3, 5 minus -1. And this is now a direction vector parallel to the vector, parallel to the plane in question. If we take just a second to think about the concept of a parallel vector that is not on the plane, so realistically what I need is that simply the distance between the tail of my new vector and the plane needs to be exactly the same as the head of my vector and the plane. But this vector doesn't necessarily need to be pointing this direction exactly, okay? It can spin, it can rotate around and around and around and around. It could point any direction really. And it could rotate, 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 as long as at every point this distance remains equal, if that makes sense. So my drawing, of course, is kind of difficult to understand, but it can rotate around this point as long as it stays level in relationship to the plane that is there already. Hopefully that made a bit of sense. So I'm looking for a vector that does that, and if I think about how planes are defined, I have one vector on this plane. If I draw another vector on this plane, okay, then two vectors, any two vectors in the whole world define a plane. Only one plane can be drawn that contains both of the vectors, any two vectors. Now, if I have two vectors, I can also find their normal vector. That is a vector orthogonal to both of them. So in this case, if they are forming a plane, then the normal vector is either going down from the plane or up off of the plane, okay? Now this vector is now perpendicular to this vector and to this vector, okay? It is perpendicular because these guys form a flat surface. The two blue ones form a flat surface, and then red is coming up off of the surface or down from the surface. Okay, that's helpful. Why? Well, because now, since the red is orthogonal to the blue, any vector that exists that is orthogonal to the red vector will be parallel to the original two vectors, which means that it's parallel to the plane. So it doesn't matter how my new vector is, it just matters that it's orthogonal, it's perpendicular to the red vector, and that will make it parallel to the blue vectors, if this is making sense at all. This vector could spin all the way around. And as long as it's still perpendicular to the red vector, whichever direction it's pointing, spinning around that red vector, the red normal vector, as long as it's perpendicular to the red normal vector, it will be parallel to all of the blue things here, the blue vectors and the blue plane. In our last lesson, we learned how to create a normal vector. We did it in 2 dimensions, so it was normal to the line. In this case, we're going to be normal to the plane. And all we need to do then is, I believe we used lowercase n with a little cap on it, was our normal vector symbol. At any rate, that's what I'm going to use here. And we said that all I have to do is take the coefficients of x, y, and z, 1, 2, -1, and now that is normal to the plane. Okay, so now any vector perpendicular to this normal vector will be parallel to the plane. So that is using the dot product. If the dot product between two vectors equals 0, then they're orthogonal or orthogonal, then they're perpendicular. So that's what I'm going to find. So the dot product between my normal vector and the other vector that I'm going to be finding is going to be 0. So in order to do this, I'm going to sub in any two values for x and y, and I'm going to find the value of z that is going to make this statement true. So take the dot product first. I've got 1 times, and let's just let x, you know what, let's, well, sure, I'll write that. Let x equal 2, let y equal -2. I'm just choosing arbitrary values. And now we have the dot product. That's going to be 1 times 2 plus 2 times -2 plus, or negative 1z equals 0. Now I'm just going to solve for z. 2 minus 4 minus z equals 0. This is -2. Negative z equals 2. Z equals -2. Therefore, the vector 2, -2, -2 is parallel to the plane. And I just went back and double checked it. We just use a lowercase n with an arrow. It's the normal vector. So I just want to talk quickly about how to define a unique plane. When you're working in 2-dimensional space and you're defining a unique line, you simply need 2 points, right? Any 2 points. There's only one line that could possibly go through both of those points, okay? Both of these points have coordinates x, y that serve as solutions to the equation of the line. Now, in 3-dimensional space, if you're given 2 points, you can define a plane, but there are actually an infinite number of planes that can be defined by those 2 points. And you can kind of see that here in the picture. The blue, if you just rotate it, it becomes green. If you rotate it, it becomes red. And any plane in between this, along this rotation, possesses these same 2 points. So that's not enough information to define a unique plane. If you had a third dot, and it was just along this, or sorry, by the same token, if you had a line, you could get this plane to contain this line, but there's an infinite number of planes that also contain that line. You essentially just rotate the plane around the line. So that's not enough. So we need a bit more. Well, what do you need? There's a handful of other options. One of them is pictured right here, and it is two intersecting lines. So if you have two non-parallel directional vectors, they will intersect. So here they're directional vectors, so they kind of intersect right at the origin. So that's easy to see. They'll create, just like our axes would create a plane, these two intersecting vectors create a plane. Now, that's not the only way to do it. Another way to do it using vectors would be to have two parallel vectors. If you have two perfectly parallel vectors, they will also form a plane. You can think about if you were holding two pencils in your hand and you made them perfectly parallel to each other, you could fit a flat surface. You could sit a flat surface on them, and if the flat surface was glued to the pencils, then you could turn and move the pencils in the plane however you wanted. As long as those two pencils stayed parallel to one another, they would continue to define a unique plane together. The reason they need to be parallel is, for instance, you couldn't have one vector going this way and one vector going that way. In order to accomplish that, you would need the plane to curve, at which point it would, or twist, at which point it would cease to be a plane, because a plane is a flat surface. So two parallel vectors will define a plane. And then probably the most common way to think about it is three non-collinear points. So 3 points that do not all lie on the same line, like we had talked about up here. And you can picture that kind of by holding your hand out. If you just hold out your thumb, your pointer, and your middle finger, and you can move those fingers around, but no matter what you do, you could press a flat surface up against your three fingertips, your thumb, your pointer, and your middle finger. So 3 non-collinear points. That also brings you to another option. Well, we know that through any 2 points, you can draw a line. And so now in this situation, we have a line and a point not on that line. So that's another way to build it, either 3 collinear points or kind of by the same reasoning, a line and a point. So for instance, if we had up here this picture with, if we had this situation again where we just have 2 points, but if I drew another point up here, then that would help us to define that blue plane. Now it can't be the red plane or the green plane, it has to be the blue plane. Okay, so different ways of defining a unique plane, and a lot of it is just checking, okay, does this actually accomplish what I wanted it to accomplish? Okay, to get our equations of planes, we've done this a bunch using already our scalar equation, which is our standard equation. So the scalar equation is a times x plus by plus cz. Often you can also do plus d with no coordinate parameter, and that equals 0. That's our standard, that's our scalar equation, that's what we've been talking about so far, okay? Vector equation, you can also write planes, equation for planes in a vector equation. In this case, again, we're going to have 2 forms, just like we had in 2-dimensional space with vectors themselves. Here we have the direction, the position vector r is equal to the position vector r naught plus some multiple of a direction vector plus some multiple of a second direction vector. So we said that a plane needs to have 2 vectors to kind of define that plane. Now this plane is kind of easy to see. It goes infinitely this way, this way, this way, this way. And if we have this other RO, this other position vector, dictates a point on the plane. And so if we have a point on the plane, then we can go from that point, we can go infinitely this direction, infinitely that direction, and infinitely that direction, and infinitely that direction, and that will identify the plane itself, okay? That's what this kind of means. And we can write that in another form. We have x, y, z is equal to x naught, y naught, z naught plus some scalar multiple of a direction vector and some scalar multiple of our second direction vector. And again, these A and B are these two vectors that define the plane, and this x naught, y naught, z naught is just a point that is on the plane, any point on the plane. So if we want a kind of basic list of notes for what each of these pieces are, you can do this as bullets. I'm just going to do it like this. I've got A and B. These are non-parallel direction vectors. Non-parallel direction vectors. And these guys have to be parallel to the plane, okay? They have to be parallel to the plane or on the plane. Then you have T and S. These are just scalars. It's just changing the magnitude of these direction vectors is really what it is. And then we have this guy, which is a position vector for any point, any known point on the plane. So this is position vector for a known point on the plane. And then this original one, the vector r over here is x, y, z. Over here, this is a position vector for any point on the plane, known or unknown. So position vector for any point on the plane. Basically what this is saying is that you can find or determine any of the infinite number of points on the plane. Whatever pops out on this side will always be on the plane if you start with a position vector on the plane, a point on the plane, and two direction vectors, because you can go infinitely in this direction or that direction, which is why these guys don't actually have to be on the plane, because they're just direction vectors. They're not position vectors. They're free to move you in the direction that you want to go, and as long as they are non-parallel, they will define the plane the plane in question, really, one unique plane. So I'm going to try just to explain this one more time a little bit graphically. So we have a position vector for a known point on the plane, okay? This is RO, R naught. So let's just say it's a position vector. It's going to start at the origin, and it's going to a point on the plane, okay? This is R naught. It is heading to P naught. Okay, that is the known point on the plane represented by x naught, y naught, z naught. Now, we also know two direction vectors. We know the direction vector A and the direction vector B. So I'm just going to kind of randomize these direction vectors. Okay, here's going to be A. That's what A looks like coming off of point P. And here's what B looks like coming off of point P. Now, when we move in these two directions from point P, we can go in any scalar multiple of those direction vectors, okay? So let's say we're moving some scalar multiple of B, and that's going to move us from point P, let's say up like that. And now we're going to move some scalar multiple of A. So I'm going to go in the direction of A, and he's going to move us, let's say, like that. So now what do I have? I have here is S times B, and here is T times A. And if I add all those guys up, if I go the resultant of R naught plus TA plus SB, Well, what do I get? I get this direction vector right here. Okay? This is the direction vector r. And then we can also use parametric equations for planes in three-dimensional space. They will have an x component, a y component, and a z component. And x will be built, and it's, again, just taking pieces of this, right? It's pieces of this. The x component here is built from x naught plus t times a1 plus s times b1. And for t and s, you can use any letters you want there as long as they're not, you know, a and b, and they're not x, y, and z. The y component is the original y component plus the movements that y does. T times a2 plus s times b2. And the z component is starts at the original z, zo, the z component of the first position vector, plus t times a3 plus s times b3. Okay, so scalar equations, vector equations, parametric equations for planes in three-dimensional space. And I always forget, t and s belong to a set of real numbers. Let's put this into practice. We are going to consider a plane with direction vectors a, which is given as 8, -5, 4, and b, 1, -3, -2, and the plane goes through point P naught, 3, 7, 0. We are going to write vector and parametric equations for this plane. All right, so a vector equation, we're just applying what we just talked through in the notes. So we've got vector x, y, z is equal to the direction vector, the position vector, represented by our point given, point P, so 3, 7, 0, plus some scalar multiple of a, 8, -5, 4, plus some scalar multiple of b, 1, -3, -2. Parametric equation. Parametric equation. This is splitting it into its components. So we've got an x, a y, and a z. We're going to take x naught, which I'm not going to leave that there. I'm going to erase it, but it's x naught, y naught, z naught, plus some multiple of the a component and some multiple of the b component. Okay, so x naught is 3. We're going to add 8t plus s. Then we've got, in the y component, we've got 7, and then we're going to go a multiple of 5 in the negative direction, -5t, -3s, and z is going to be 0 plus 4t minus 2s. It's parametric, already reduced for us. In B, we're going to determine if the point Q, which is given as -10, 8, -6, is on the plane. Okay, we know how to do that. Basically, what we need to show is that there exists a set TS where all of these T's are the same and all of these S's are the same, such that 3 plus 8t plus s equals -10, 7 minus 5t minus 3s equals 8, and 4t minus 2s equals -6. So we're going to have 3 equations and 2 variables. So here we have negative 10 equals 3 plus 8t plus s. Our second equation is that 8 is equal to 7 minus 5t minus 3s. Our third equation is that z, negative 6, which is z in this case for point Q, is equal to 4t minus 2s. You'll see I lined up my t's and my s's already, leaving this blank. I could put 0 plus if I really wanted to hold the value there. So if you reach back into your knowledge bank, we know how to solve two equations with two variables using substitution or elimination. So the strategy to solving three equations with two variables, that's doable as well. It's actually more information than you need in some ways. But what we do is we use the first two, or any two, in order to solve for one of the variables, in order to solve for the first two variables, okay? So we're going to solve for t and s using equation 1 and 2. So use equations 1 and 2 to solve for t and s. Well, what does that look like? In order to substitute or eliminate, I want to multiply equation 1 by 3 so that I have 3 s's and negative 3 s's here, and then I can eliminate my s's. Okay, so I'm going to go 3 times equation 1. That's going to give me negative 30 equals 9 plus 24t plus 3s. I'm going to copy down equation 2 just as it is. 8 equals 7 minus 5t minus 3s. Now I can add these because I have opposite signs here. So I'm going to add. So I've got negative 30 plus 8. That's going to be negative 22. And I probably should have brought my 1's over to the other side already and just left my t's and s's on this side, but it doesn't really matter how I do it. I can do it after that. This is 16. 24 minus 5 is 19t, and my s's are eliminated. I'm going to subtract 16 from both sides and divide both sides by 19. I get t equals negative 2. Now I can sub that back into either of the two equations that I've used, equation 1 or equation 2. We'll do it with equation 2. And again, I didn't simplify first, so I'm not going to simplify first this time. 8 equals 7 minus 5 times negative 2 minus 3s. Here I have positive 10. 17, subtract that from both sides. I'm going to get negative 9 equals negative 3s. Divide both sides by negative 3, I'm going to get s equals 3. And now that I have the two parameters, t and s, I would just use equation 3 to check that this is true. So maybe we'll do it over here. Check in 3. So if I go left side, which equals negative 6, and right side, which equals 4t minus 2s, and then sub in my solutions for t and s. 4 times negative 2 minus 2 times negative 3 gives me negative 8 plus 6, which gives me, sorry, slight typo here. My solution for s was positive 3, which gives me negative 8 minus 6, which is negative 14, which does not equal the left side. And so, since there is no t and s combo that can satisfy all three of the equations, all three of these equations, then Q is not on the plane, okay? Therefore, Q, negative 10, 8, negative 6, is not on the plane, okay? So you will be able to find, right, any two points will be on a line or on a plane. You can do that, but the third one is the key to check, because if it's not, then this whole thing is not on the plane. I have to be able to satisfy all three of these equations. So if the point Q is not on the plane, how do I find points that are on the plane? I'm just going to leave our vector equation there because it's going to be helpful. And in C, we're going to find points on the plane. I'm only going to find one. All we need to do is choose values for T and S, and that will give us any other point that's on the plane. So if we take our vector equation, x, y, z, and we take our starting position vector of 3, 7, 0, and we add any multiple of our two direction vectors. So up here I could even say let t equal 1, let s equal 1. Now I've got 1 times this, which is just 8, negative 5, 4, plus 1 times our direction vector b, which is 1, negative 3, negative 2. And if I add up all of these components, my x component becomes 3 plus 8 is 11. Plus 1 is 12. My y component becomes 7 plus negative 5, that's 2, plus negative 3, that's negative 1. And my z component is 0, plus 4, that's 4, minus 2 is 2. Okay? You could do it again, letting t and s be any two values that you like, because they'll just be multiples of these direction vectors. And you'll get another position vector that is on the plane, or another point that's on the plane, I should say. So these, so these are position vectors that the head is on the plane, which means that therefore the point 12, negative 1, 2, right, round bracket, is on the plane. Last section asks us to find the x-intercept of the plane. Find X-Int of the plane. And for this we're going to be looking at our parametric equations, which we have. We have one for x, which is 3 plus 8t plus s. We have one for y, which was 7 minus 5t minus 3s, and we had a z which equaled 0 plus 4t minus 2s. Okay, and we're just finding the x-intercept of the plane, which means just like with finding a line in 2-space, we're going to set the other parameters to 0. That's going to allow us to find the t and s that make these two statements true, where y and z are 0, and then we'll be able to put that t and s up into the equation for x in order to determine our x-intercept. Okay, so here we go. We're going to take, I'm going to call them equation 2 and equation 3. I'm going to take them over here and set y equal to 0. So now I have 0 equals 7 minus 5t minus 3s. And I have, in equation 3, I have 0 equals 4t minus 2s. I'm going to bring this 7, subtract 7 to the other side. And as I'm doing that, I'm also going to multiply the top equation by 2 and the bottom equation by 3 in order to eliminate my s's here. So I said I was going to do this guy times 2, and then I'm going to take equation 3 and multiply it by 3. So this is going to be negative 7 on this side, so I'm going to have negative 14 equals negative 10t minus 6s. And this equation 3 is going to be 0 equals 12t minus 6s. Now I can subtract these guys.
Negative 14 minus 0 is negative 14. Negative 10 minus 12 is negative 22t, and this becomes 0. So now what do I have? Divide both sides by negative 22. I get t equals 14 over 22. Those are both even numbers, so this is going to reduce to 7 over 11. So t equals 7 over 11. Now for finding s, I can sub this back into equation 3. So I've got in equation 3, I have 4 times t minus 2s equals 0. So I have 28 over 11. 28 over 11 equals, I'm going to add 2s to both sides. Divide both sides by 2, I get 28 over 14, or I could just cut the numerator in half, I get 14 over 11. So s equals 14 over 11. So just because you're getting funny numbers, don't assume that you did it wrong. T equals 7 over 11. And now in order to find that x-intercept, all I have to do is sub my values for t and s into my equation, into equation 1. So here's, maybe I don't have room going down, so I'm going to put it over here. Equation 1 is x equals 3 plus 8t, t is 7 over 11, plus s, which is 14 over 11. And to reduce this, I'm going to express all of my terms over 11, so 3 becomes 33 over 11. 8 times 7 is 56 over 11, and 14 over 11. 56 and 14 is 70, plus this guy is 103 over 11. So the x-intercept is exactly 103 over 11. That is where the plane crosses the x-intercept. Again, we used the knowledge that the x-intercept will be found where y and z are 0. So we set y and z equal to 0 and then used those as our two equations to solve for our two variables, t and s, and then we just subbed our two variables for t and s back into equation 1 in order to determine that x equals 103 over 11. All right, example 3, we're going to write equations of planes, and then we're done. This will take about, looks like a little more than half a page. So we're going to take a vector equation and a parametric equation for each. So we're going to start with A. We're given a plane, and we're given the x-intercepts. So the x-int is 2. The y-intercept is 4. And the z-intercept is 5. We're going to first find a vector equation and then a parametric equation. So the first thing we want to do here is use the intercepts. So we have to talk about what is a vector equation built up. Well, it's built up of one point that is on the plane and two direction vectors, okay? So we have 3 points, right? This is the point 2, 0, 0. This is the point 0, 4, 0. This is the point 0, 0, 5. So I have my points, that's not a problem. Now I need direction vectors. Well, the direction vectors can actually be built by starting at one of these points and then getting to the other points. So I can go from my x-intercept to my y-intercept, that will give me a vector. Then I can go from my x-intercept to my z-intercept, and that will give me a vector. And they intersect at the x-intercept. So that'll be my two direction vectors for the plane, okay? So let's call, we don't have the name of these points, so I'm just going to call them vector A. And we're going to go from 2, 0, 0 and head to our y-intercept, 0, 4, 0. I'm going to solve that out, and then we're also going to do vector B, do them kind of at the same time so that you see what we're thinking through. 2, 0, 0 minus, and this is going to head to our z-intercept, 0, 0, 5. All right, well, 2 take away 0 is 2. 0 take away 4 is negative 4, and 0 take away 0 is 0. So this is now one of the direction vectors that's going to define our plane, help us define our plane. Here we have 2 take away 0, we have 0 take away 0, and 0 take away 5. There's the second direction vector. Now for a point on the plane, I can use any 3 of those points. So let's use, this one doesn't matter, use 0, 4, 0 as a point on the plane. And now we can get to writing our vector equation. X, y, z is equal to 0, 4, 0 as our position vector, plus some multiple of direction vector 2, negative 4, 0, plus some multiple of direction vector 2, 0, negative 5. Now this equation is not unique for this plane. We could have used different vectors and different position vectors and different direction vectors and gotten a different equation, but this is an equation for this plane. Corresponding parametric equations. So I'm just going to take them right from our vector equation. X is 0 plus 2t plus 2s. Y is 4 minus 4t plus 0s, so I don't have to write that. Z is 0 plus 0t minus 5s. There's parametric equation. And I'm going to clear this to make room for B. So in B, we're again going to write a vector equation and a parametric equation. This time it's going to give us different information. We're given that the plane contains the line x, y, z is equal to 0, 3, negative 5 plus some multiple of the direction vector 6, negative 2, negative 1. That's not enough to define a plane. We're also told it is parallel to the line. So that's interesting. So this first line is contained on the plane. Second line that it gives us is parallel to the line, parallel to the plane. So contains that one. It is parallel to x, y, z. We're going to get another line here. 1, 7, negative 4 plus some multiple of 1, negative 3, 3. Now this is where we really need to be able to understand what's happening here and dissect the information. There are some things that we know. If the plane contains this line, and this line is defined by this position vector and this direction vector, okay, then that actually means that, I say since the line, I'm going to just call it line 1. Let's do this, line 1. Let's do this, line 1, line 2, so that I don't have to write it out. Since the line 1 is on the plane, the point 0, 3, negative 5 is on the plane. Okay, if this position vector has its head on the plane, then the point 0, 3, negative 5 is on the plane. Okay, well, when we're defining a plane, we need a point and 2 non-parallel vectors. Okay, well, let's talk about this. If the line that is contained on the plane heads this direction, then that can be one of our direction vectors. Okay, but now we also know that this second line is parallel to the plane itself. That means heading in this direction will keep us, if we start on the plane, then heading in this direction will keep us on the plane. Does that make sense? So if we use this position point and this direction, you're parallel to the plane. That means if we started with this position vector and headed in this direction, we would be on the plane. This new line would be on the plane. So also direction vectors t some multiple of 6, -2, -1, and some multiple of 1, -3, -3 can be used to define the plane. So we're pretty much done with this one then. The vector equation is going to be x, y, z. It's defined by the position vector 0, 3, -5, because the point 0, 3, -5 is on the plane, and then we're going to head in these two directions, some multiple of 6, -2, -1, and some multiple of 1, -3, 3. Okay, putting together a parametric equation for this. X, y, z. X is 0 plus 6t plus s. Y is 3 minus 2t minus 3s. Z is -5 minus t plus 3s. Done. One thing I didn't do that the book does do, since they used t and s to be these scalars, I can't technically use them here and here. So they switched those to k and l, or any two other letters, which would switch all of these to 6k plus l, 3 minus 2k minus 3l, and -5 minus k plus 3l. That makes a lot of sense because this t wasn't necessarily equal to k. That's not fair. But this k and these k's are all the same, and this l is all the same. Alright, ladies and gents, we are finally done with this lesson. Your practice problems are found on page 451. You're responsible for the knowledge needed to take care of questions 1 through 13. Thanks for watching.